But happy day is coming day after tomorrow, the final. This is what we talk about. Just a short review, and again, there's a nice app which helps us to visualize how a radioactive decay is happening here. Radioactive atoms of one type disappear, and normally actually radioactive atoms of another type appear instead. And where is it? The number of initial number of radioactive elements decrease in time, and we have two different equations to describe. They look differently. Mathematically, they are absolutely identical. It's just algebraical rearrangement. And this type of equation convenient to be used when the numbers represented by some power of 2. Otherwise, that type of equation usually is more convenient. And an activity, the number of decays per second, decreases in the same manner, because by definition it's just a product of lambda and instantaneous number of radioactive nuclei, and lambda in this expression is not a wavelength of anything, even it's the same letter. That's a decay constant, has been measured for all materials. Well, and in physics, when we say this word, the decay, it doesn't mean gradual decline in something like let's imagine this is an atom of uranium. That's not a decay. Yeah. In physics, a decay is something like this. That's a decay. When it happens, after that, we have no original element anymore left at all. What we have is, well, pieces of that, like this, or this. Want to see it again? No? It doesn't have any feelings. Well, the question I want to ask is about the relationship between these two different but related variables, quantities. One has a name half-life, second half-time, and just to illustrate again one important fact, which was at the bottom. During the decay, most of the stuff remains inside of a system. Come on. Today is a Caesar's Day. That's the question. So we can imagine we have, again, we don't need this anymore, many different in space, different in space, but same material atoms. What a decay means, that's what it means. Some might fly away, but most of them remain inside. Oops. My decaying device. Oop. See? Split. Sometimes two. Sometimes at the same time. They might, several of them decay at the same time. We just have to count. Eventually, of course, exactly a half of initial amount remains in the system, but then it keeps decaying. And to describe this process, we can use either one variable half-life or another. Let's check. Take this back. Thank you for bringing it back. Well, let's see a distribution. One, two, three. No one says 7 because it's not related, it's not specific enough. Something is unfair, something is fair. So you should have asked what? Well, of course it's about just a mathematical exercise. The relationship between these two, well, first of all, a definition. Yeah. That thing we call lifetime is just the decay constant inversed 1 over the decay constant, and that thing we call half-life. That's how the graph looks like. It's related to that, and the relationship is like this or like this. But the graph actually helps to understand what is happening, because this equation tells us that the half-life, again, is time we need to wait until we have left with a half of the initial. But if we write the same law using the exponential form, and number e is about, well, 2.7, like it's like almost 3. So we need, that's what I want to write. We need to wait longer time until more atoms will decay, until we have left with only about a third of initial. And that's what we can read. And this was the last slide, and we have solved this problem by counting. But of course, we should solve the same problem using the direct approach. What could we do with the equation? Well, the only kind of tricky part in this situation, just to illustrate how equations work, is this. This sentence, last atom decays, says that no atoms left. Nothing, yeah, left. That means the final number we're rooting for is 0. Question is, can we use this equation to calculate how much time would we have to wait? until it gets to 0. The equation would have been one hour. Yeah, 1 hour. That equation, theoretically, again, depending on the philosophy, has no solution or has a solution with t equals infinity. But that's not a case. This is just an illustration of the fact we can't use 0 for the number of elements. What we could use is n equals 1 and calculate how much time using that equation. How much time should we wait until one atom remains? That equation is solvable. 1 is equal to 128 times 2. Well, I just use this variable n, which, as we know, just represents how many half-lives can we fit in that time interval. And we can solve it. 2 to the nth will be equal to 128 over 1. Now, 128 represents the 7th power of 2. And now we can make a conclusion. N equals 7, so we have to wait 7 half-lives until only one atom remains. Well, but still, on average, we have to wait one more half-life until that last atom also disappears due to a decay. So these are just different questions. Yeah. How much time should we wait until nothing left, and how much should we wait until something is left? Something always is represented by a specific number, which can be used as a part of the equation. And, well, if we want to solve this equation, 1 is equal to 128 times or, again, mathematically absolutely equivalent. We could do it. We just need to know the decay constant. And, well, if half-life is equal to the natural logarithm of lambda, the lambda will be equal to the natural logarithm over half-life. And for us, it's an hour. So if we keep hours, this is how we could write it down. How, again, just an example, how would we solve an equation like that? Well, I personally don't like negative exponents, so I multiply both parts of this equation on the exponent which is opposite to this, and that gives me this equals 128. Now we can apply the natural logarithm to both sides of the equation, and ln e to any power becomes equal to that power. That's a mathematical review. So natural log of 128, and the time we've been waiting for would have been this, and calculation will give us again 7 hours, of course. We don't have to use any calculation like that, again, if the initial number of atoms is a power of 2, because again, there's much faster and simpler way to address that mathematically. Okay, question. In a problem like that, that word now always means when we start the stopwatch, t equals 0. From that time forward, the number of radioactive elements of that particular type decreases in time, and initially we have 1024, which is actually the 10th power of 2. If we wait 1 hour, we have left 64 of those. 64, which is the 6th. If we wanted to, if we needed to, we could calculate how many actually did decay. Those are different questions. How many left? How many decayed? The law of radioactive decay relates directly, in any form, directly the initial number of elements and how many left. But how many decayed, of course, is just the difference. So here, that's not a part of the reasoning. I'm just giving you time. Now, so we can solve an equation. 64 is equal to 1024 over 2 to this power, and this number n tells us how many half-lives have passed. If we know this number, we can reverse the calculation and calculate how much actual time did pass. So it depends on what we know what we're looking for. In this situation, we actually don't even have to solve this equation, but we will. So 1024 divided by 64 supposed to be equal to, oh, today is Wednesday, right? An extra burden. So, then 24 over 64 is 2 to which particular power? Fourth? So that's going to be 16. 16 is 4 times 4, 2 times 2 times 2 is fourth. So n is supposed to be equal to 4. Or we could have done this, 1, 2, 3, 4, which might much faster and doesn't require lots of writing, as long as we remember powers of 2. So, and that is 1 hour. So 1 hour is supposed to be equal to 4 half-lives, which means 1 half-life is supposed to be equal to 15 minutes. But if we use our set of answers, 15 minutes is supposed to be equal to 2 hours divided by 8. Which means the answer is supposed to be 8, technically. One more question. Just do it. You really need a laser pointer. Which one? This? This? And what the question? That's a definition of number n. Go away. Okay. I answered that's a definition of this variable n. A definition, what is it? What is a definition? Did we have that discussion in this course? Or it was 105? 105. Let's have this discussion. What is a definition? What do you think? We have a conversation. Yeah? What is a definition? You asked me a question, I answered. That's a definition. Now I'm asking you a question. What is a definition from your point of view? It's an important part of a scientific reasoning in general. Not just physics. Every science is based on specific definitions. But what does it mean when we say this word? That's the source of your confusion about this number. So, what is a definition, anyone? Yes. Yep. It is an agreement. Someone has it invented, made everybody agree. Made means it worked for everyone, it was convenient, it stick, and that's it. And now everybody has to use the same statement or equation. And this is a number of time intervals we call half-life, which we can fit in any given time interval, which we measure using clock. It's like measuring distance. You cut it in pieces and you see how many pieces you can fit in it. But this particular piece of time has a name, half-life. And we count 1 half-life, 2, 3, 4 half-lives can fit in this time interval. And t is a running variable. Yes?
For the half-life, should it be 15 minutes or 25?
1 hour divided by 4, 15 minutes. But the format of the answers presented was different. So there's one additional mental operation which is supposed to be done to choose the correct format. That's it. Yes? When I use this? Well, I see. This equation mathematically is identical to this equation. So that's an algebraical fact. It's like looking at the same person from two different perspectives. But in order to see or to prove that these equations are mathematically identical, there has to be some actual work done, which requires certain time. And there is a slide I don't know, somewhere in the middle of the last lecture, there is a slide with exact calculation. You should just look it up. This is absolutely identical, mathematically identical situation, no matter what equation to use. It's a matter of convenience. And when, again, that's a rule of thumb. It's not a law of nature. When the initial amount is provided in the form of a power of 2, in that case, the law of radioactive decay in this form will be more convenient. That's it. However, it doesn't mean we always have to do it. We could have used a law in this form. That would require a little bit longer calculation because we would have to use logarithms. Do you like using logarithms? To use logarithms. That's going to be just a little bit longer type of work. A couple of more lines. That's it. So, in this situation, you just need to repeat the type of reasoning. Again, choose, hopefully, correctly. The answer, we start again from the same amount of radioactive nuclei. However, now the question is different, and that makes difference. So I read and I underline important numbers. Then I make a choice. What equation do I want to use? This one or this one? And because the initial number is a power of 10, I choose this. Now I write, okay. Now I stop writing because I need to correct my 4.
That'd be 16 instead.
That's why I walked. You saved that gentleman from a question. So, I made a mistake, so many in my life. That's wrong, because our word, how many will decay, the law directly relates the initial and how many will remain. Yep, so this is what we need to do. 1024 minus the number of decayed should be equal to initial divided by this. And so, well, What do we have for n? Six. Yep. No? Okay. That is 16. So basically 1, 2, 3, 4, 5, 6. That's it. 6 half-lives. And that means time we are looking for is equal to the number of half-lives time a half-life, which is 6 times 10 minutes. That gives 1 hour. Well, okay, no questions. Just let's practice in a different form. Just a second. This is what I want to change. I just realized I don't like this number. I like 127 hours. You know it's going to be posted and videotaped. So, new number, 127 hours. And the activity decreased to, and I know that. The next slide is practically identical. How do I know? I wrote it. With one different word, by. So that's what the point of this exercise. Mathematics is simple, the same, but we need to, again, imprint the difference between 2 and by. What does 2 mean? It means we start from, well, 100% of activity and eventually we reach 68% of initial value. And we need to wait 127 hours for that to happen. So the equation we need to solve 68% of 100% times. Clearly those numbers don't represent any powers of 2. That's why I use this general equation. So this is what we're looking for. Just try to be more accurate in general. Natural logarithm of 100 over 68 divided by 127 hours. I don't have a calculator today. So that's going to be some number. Someone just tell me the number. Do you have it? For the lambda, yeah. 0.003 if we use hours. So, and a different situation when there's one different word. What does it mean? It means that now, if we start from 100% of activity, this difference should be equal to 68%. That's it. So the equation now is technically percent is equal to 100. So well, just as an exercise, we can calculate it in seconds. Because we know how many seconds in 1 hour that will be in seconds. So I'm gonna give you some time. This problem is directly related to a very important dating mechanism. Yeah, well, dating in physics is different from dating in life. This means measuring time passed in thousands of years, usually. When every living object on the Earth takes oxygen inside, it also takes a certain number of carbon, including carbon-14, which is radioactive. So every living tissue in trees, animals, bones, has a certain amount of radioactive carbon-14, and it decays in time. So we can find a sample of something, a bone, a piece of wood, which is very old, but we can use a Geiger counter and measure its activity now. And there is an assumption. Some people don't believe in that assumption, but most scientists believe that when that wood was alive thousands of years ago, it had inside it, on average, the same amount of carbon-14 atoms as currently living wood has now. So that's what we can do. We can walk to a forest, cut a piece of wood, which has exactly the same size, of course, same wood, as we found, and then we can measure its activity now, and we make an assumption that this old wood with the lower activity had the same activity many, many years ago. And that gives us two activities, the initial and the final. And since we know the half-life, the lifetime for carbon-14, we can calculate the age of that sample. And in this situation, well, so 0.22, that's the activity now. And again, now of old, and the 0.88 is the activity, which of course we measure now, but of fresh. And we think that this old, when it was fresh, had the same activity. That's the idea. So we can relate now these two activities by the law. Well, in general, we can write it like this. However, if we assume that we're going to get some convenient numbers, powers of 2, we can write the same law differently. And if we solve this for n, what do we get? Two. That's the first part of the reasoning. And since we know the half-life of the carbon, 2 half-lives means time will be equal to n times half-life, 2 times 5730 years, or 11, yep.
How do we make the assumption to use that it will be a power of 2? What helps us to decide if we can make that assumption?
Numbers like 2 or 8, 4, 16, 64. It doesn't really matter in the end. But all technical problems on carbon dating, they're all based on this assumption. Yeah. If you have to solve a problem with some weird percentage, 68, 75, well, 75 actually 3/4, so, but you know, some weird random percentage, in that case, that wouldn't be a power of 2 usually. Yeah. So, so 11.5 thousand years, and the question I want to ask you now is related to the last part of this problem. So, a similar situation, 75%, for 75% decayed. Activity now is 10 to the 9th, and we need to calculate the initial activity, so we have to solve the same problem backwards. But there is a question about the mass of the sample, that piece of oak or bone which has been unearthed. So here, that's the most important word. If 75% decayed, can we use this equation? Well, whatever. No. That should be this equation, because we only can relate directly the amount of left. And 25% left, it means 1/4, yeah. And number 4 means count halves. So it's supposed to be n equals 2. That's exactly the same situation, exactly the same problem. We just have to solve it backwards. Now, activity R will be equal to initial activity divided by, well, 2 to the n, so initial activity divided by 4, and activity we measure now is given. So the initial activity is supposed to be equal to 4 times 10 to the 9th. It was a bad choice for numbers for today. BQ, decays per second. So, and what about the mass of a sample? The mass of the sample this question is related to this demonstration. The vast majority of all elements before and after the decay remains in the sample, remains in the system. So since they stay in the system, It doesn't change the mass. And what else can we talk about? How many? Okay. How many carbon-14 atoms provide activity? Well, technically, that's the relationship between activity and the instantaneous number of atoms providing that activity. The activity is equal to this. That's what we are looking for. That's what we could have called the initial number. It was 11,000 years ago. So if you want to calculate this number, all we need to do is this. But of course, for that, we need to know lambda. And Five 734. Keep forgetting this number. Or 537. 573. Actually, yeah. 573. It's rounded. Years. And if the question would have been about lambda, we could use years. But when the question is about number of atoms, and we're using big U's, so that big U over lambda, which means 1 over a second, we cannot use mismatched units. We cannot use seconds and years in the same equation. So we have to, that's years. 365 days in a year, 24 hours in a day, 3,600 seconds in an hour. That's going to be our calculation for this number. So n will be equal to 4 times 10 to the 9th divided by lambda, so divided by 0.7 times 5730 times 365 times 2, 4 times 360. What unit do we have for a number of numbers? Number of atoms? We have no unit. So seconds and seconds getting canceled here. So total mass of those, well, if we need to calculate the mass of a material, we have different approaches which came from your knowledge of chemistry or common sense. If we know the atomic mass and the number of atoms, we can just multiply these two numbers. So the atomic mass of carbon-14, well, it's carbon-14, so it's going to be close to 14. So many fours today. 14 atomic units. And the number is about 10 to the 21st. And of course, we could keep atomic units, but we also can calculate grams, kilograms. If we use just a conversion factor, 1 atomic unit is about 1.6 times 10 to the negative 27th. times 10 to the 21st. That's going to be kilograms. And that is a tiny, tiny number. Remember, we started from a sample which mass was 400 grams, almost a half of a kilogram. And this we're going to have milligrams. Of course, because carbon-14 composes only a tiny portion of the whole carbon, and carbon actually composes only a tiny portion of the whole wood or bone. So, but you see, if we measure masses, those are tiny, but the number of atoms still huge. Any questions? These are just illustrations of different type of calculations. I think I'm missing a couple of nines in there, but well, I'm gonna give you time to start. How would you approach this situation? If we get 1 kilogram of uranium-238, first of all, you would go to jail. You have to be well, you have to be a physicist, have to have a security clearance. And then you would get it, and you would get radiated, and you would die. And unfortunately, many people who begin, people who have begun study radioactivity, they didn't know at the time the danger of radioactivity. They've been carrying in pockets radioactive elements. So they all ended badly health-wise. Unfortunately, physics might be dangerous. Well, you saw yesterday, until recently, people have been using Fiestaware for food. Those plates had uranium salts to make them beautiful, beautifully red. And still you can buy online, you can find some, plates still radioactive. Well, half-life. That's this thing. Years. Seconds. I know I need to do that because I need to relate an activity and well, eventually the mass, but there isn't an equation which directly relates activity and mass, so we got to start from an equation which directly relates activity and the number of radioactive atoms of uranium. But how would we calculate the number? Well, total mass of this sample should be divided by the atomic mass and I'm not going to do all the things, so 4.476 the first part 1. Well, if I use kilograms, I have to convert atomic mass into kilograms, and for uranium-238 you can look it up, but of course it's going to be close to 238 U's. Oops. It is what it is. Now we can just take a calculator and finish, and I'm not going to do it now. This is the exactly same calculation we just have done recently, but backwards. Yeah, from activity to numbers, from numbers to activity. Now, we have talked about a decay in general. However, historically and physically, they've been studied 3 very important types of a decay. At the time of the study of this phenomenon, people didn't actually know the nature of those particles, so they just call them alpha, beta, gamma. Later, they figure out that gamma turns out just very energetic photons. Alpha, a nucleus of a helium atom, which has 2 protons and 2 neutrons, and beta, original beta, negative beta, turns out to be just electrons. And to figure out that those particles have charge or don't have charge, they applied magnetic field. So we know if particles travel through magnetic field, if they don't have any charge, they shouldn't be deflected. But if they have a charge, we can apply right-hand rule to figure out what kind of a charge, positive, negative. And we know that if we measure the curvature, we can calculate the charge to mass ratio, for example. Then we can collect that very complicated chemical process. You can collect, let's say, all alpha particles somewhere, weigh them, calculate the mass, and if you know the charge mass ratio and mass, you can calculate charge. So it's been done, of course. And again, from historical reasons, people have invented many different symbols for exactly the same things. So we have to know those symbols. For example, electron, photon, alpha particle, proton, neutron. And after soon, relatively soon, another beta particle was found. They called it beta because it has exactly the same mass, but it's positive, so they called it a positron. And very often, if you read the symbol, it doesn't show you the numbers related to its mass or its charge, just a letter. But we need to know that this letter represents a very light particle, 2,000 times lighter than a proton. So we set the atomic mass number to 0, but it carries a positive charge, 1 elementary charge. And a proton is heavy, so atomic mass number for a proton is 1, Z is 1, a neutron is neutral. And here we have an example of a typical radioactive decay series. Normally, when the first decay happens, the new particles also radioactive, so eventually they decay, and those decay, and those decay, until some stable not radioactive isotope finally is reached. So, what do you think? What do you think should happen to the mass during a radioactive decay in general when a nucleus decays without any external force acting on it? We call it a spontaneous decay. It's a type of a nuclear reaction, but people sometimes reserve a word reaction for a situation when we had induced it. We're going to talk about it very soon. So, imagine, take like uranium-235, which also is radioactive, decays much faster than uranium-238, makes plutonium, which can be used to make an atomic bomb or power plant. And it sits, and then boom, splits. What should happen to the masses? Well, it's basically a question about our intuition. We already had a very similar situation when we needed to compare two masses, a mass of a nucleus and the mass of individual particles which we needed to use to build it up. In a way, this is a similar situation. And I'm not rooting for any records today, but it's going to be a couple of more questions, I think. On a microscopic level, any reaction happens with the change in the mass. Because of what? Because of the Einstein equation, which relates energy and mass. And energy changes, and if energy changes, the mass changes. In this situation, if you imagine again what's happening, you know what? I want to do it again. Now I'm going to do it with plutonium. First time it was uranium. This is plutonium, you see? It is at rest. That's important. You knew what would happen, right? So why? So scared. It flew away. If the object was not moving and then it is moving, what does it tell us about energy? Kinetic energy is not zero anymore. So kinetic energy was zero, and now kinetic energy is not zero. So there is a certain amount of mass, according to this equation, which should be associated with that kinetic energy. Total amount of energy shouldn't differ. So if we calculate the amount of energy related to the mass number 1, the mass number 2, the mass number 3, supposed to be difference which results into the motion. Technically, the law can be written like this. There is a certain amount of energy stored in the mass number 1, and then there is a certain amount of energy mass number 2, mass number 3, but also there is a certain amount of energy due to the motion. So if we calculate that difference, well, that's what we can call the energy before related to the mass before, and that is the amount of energy which we can call energy after the reaction, after the decay, which is supposed to be related to some total mass after the decay. The difference will tell us how much energy has been released in the form of motion, in the form of kinetic energy. So when the spontaneous decay happens, we can use two very important conservation laws, law of conservation of energy, but also electric charge should be conserved always. So this tells us how we relate situation after the decay with the situation before the decay. So this is a standard term for a particle before the decay, a parent particle. And for a standard symbol for any element, we always have the atomic mass number and the atomic number A and Z. What should happen? Well, dotted particle number 1 please call in an hour. Some people just don't listen. I tell everyone, I can't talk until 11. No? So Z1, A1, dotted particle number 2 has Z2, A2. But the law of conservation of charge says this. It must be conserved. Or maybe even 3. Dotted particle number 3, why not? Still has to be conserved. Now, the amount of kinetic energy is usually much, much, much smaller than energy stored in the mass. So it doesn't affect the mass number. So it also will be conserved. And now we can solve any equation related to any nuclear reaction. This is a spontaneous reaction. Parent particle decays in 2 dotted particles. Conservation of charge, conservation of energy. And now we can use this to analyze all 3 types of a decay. Gamma. It happens when an excited nucleus drops from high energy state to low energy state, changes energy from high to low. So the energy change, of course, leads to a highly energetic photon traveling away, and that's what a gamma rays, gamma decay is about. And we have 2 types of beta decay. Beta minus, when an electron is being one of the results of the decay. Beta plus, when a positron is one of the results of the decay. And of course, since law of conservation of charge and law of conservation of energy work for any reaction, we can immediately write what should other dotted particle be at the result of this reaction. And there is one more particle which being released in a beta decay. We call it a neutrino. It has no charge, but it's practically undetectable. It's very, very hard to detect it. So we just neglected this equation. This shows it. It's a Greek letter nu, a standard symbol for a neutrino, but we can always just ignore it because it's almost undetectable. It doesn't practically affect energy of the reaction. So how would we solve this situation? Carbon 14, we know it's unstable. It decays on average in 5,730 years. And we know, because we can apply magnetic field and see that electrons should be traveling after the reaction happened. So we have to add that symbol right here, right now. That's supposed to be the electron, which is very light, but has a negative charge. And this is supposed to help us to finish the reaction. What's supposed to be the unknown element B in this reaction? You have a periodic table right in front of you to see the symbol. But of course, the most important part is what? Getting those numbers, A and Z. A, that's easy. First of all, we can ignore the presence of neutrino. So A is supposed to be equal to 14 minus 0, 14. But A doesn't tell us the location of this symbol, of this element in the periodic table. We need Z. Z is supposed to be equal to whatever we have here, minus what? Or plus, it depends how you write it. Minus 1, actually, or plus 1, or plus negative 1. I don't know how it's clearer. So carbon, what number should I write for carbon? 6. So that's supposed to be 5, and that's supposed to be a nitrogen. Was it a beta plus? Did I change it? Carbon 14 decays I don't want to mess it up. Is it a beta minus or a beta plus? I don't remember right now. No, I think it's supposed to be beta minus. In that case, that's supposed to be 6 equals Z plus negative 1. Yeah, you're right. That's supposed to be 7. You know what? I don't like things unclear. All right. One last minute. Now I doubt myself. Beta plus or beta minus? beta decay, but it doesn't say plus or minus. I know it's beta. So it's supposed to be plus. So I don't know why did I change it. Just problem, yeah, I knew. So it's supposed to be plus. Because it's supposed to decay into nitrogen. All right, plus.
It wouldn't work if it's plus, because you need to maintain A on both sides. So A is 6 on the left, carbon. And for nitrogen, A is 7. So you need A to minus.
Where is nitrogen?
So right.
Sure. I was right. I was always right. All right, so I was always right. That's a relief. But now I have no time to finish this calculation. I'm going to do it tomorrow. I'm going to finish this calculation. But today is a special day. Very special day for you, because now you can. What can you do now? It's always a day before the last day, so I need a volunteer, anyone who will spread it around and collect and bring back. And as you know, I can't remain here, so I can leave it. I just need to save this slide and this presentation so I can post it for you.
Do we have to go to the lab today?
Get here.
Do we have to go to the lab? No.
The syllabus says that the lowest lab grade will not be included in the final calculation. I don't know how many labs did you do, so I can't answer your question. That's it. That's what syllabus says. The lowest lab grade, only 8 best grades out of 9, will become a part of a calculation. So please, someone has to start doing it. Just open the envelope, take the evaluation sheets out, spread them around. Please, anybody. I'm leaving. I'll be back tomorrow. But right now I have to leave. It's a policy. Show that. I do have office hours later today, so if you have any questions.
Yeah, I have an iPad. I'm going to office hours for a couple of them. Yeah.
I'm doing laundry with Kendra later.
Oh, okay. Just let me know. I think Kendra wants to do work too, or like hang out.
Yeah, I'll let you know.
Cool. 2 days.
Yep, bye. Yeah.
I can take those for you.
Perfect. They're all here.
Where should I take them?
I think that the physics department is on the next floor. Office has a very pretty outside glass and it says physics.
Yes.
I'm pretty sure that's.
With all the math on the outside?
And I think that's weird. If not, I'm sure someone will be like, people do this all the time. Bring it to X, Y, or Z.
All right, I got it. Thank you.